So, my first experience of having math be an art was when I was working on my homework sometime in middle school. So, I was working on my homework and I was really stuck on this one problem. And when I took it to my dad to see if I could get some help with it, he was like, "Oh, yeah, but like in order to solve this problem, you need to know that all of the interior angles of a triangle, so like if you measure all of these angles and add them up, they always add up to 180 degrees." And I could have just taken his word for it because my dad's really good at math and could have just believed him. But this was where my experience of math being an art started, because rather than taking it as fact, I said, "I don't believe you. Like any triangle, no matter what the triangle looks like it always adds up to 180. I'm not sure if I believe that." And my dad was like, "Well, why don't you try it? See if it actually does work." So I got out my protractor and I drew a whole bunch of triangles. And so, like, I drew an obtuse triangle like this and measured these angles. I drew a really long, skinny triangle like this, and I measured these angles. And sure enough, when I added up all of the angles of any triangle, they always added up to 180 degrees. And then my exploration of math as an art continued, because even though it wasn't required for my assignment, and like it wasn't anything I needed to know, I got curious and I wondered, well, if that's true for triangles, is it also true for squares? And so I tried it out and I said, okay, well, obviously, like with squares, you have four right angles, which are each 90 degrees. And since 4 times 90 equals 360, it makes sense that all squares would be 360 degrees if you add up their interior angles. And same thing with rectangles, because the only difference between rectangles and squares are their side lengths, but their angles are still all 90 degrees. And I was like, okay, so that's true for squares and rectangles, but is it true for all quadrilaterals? Because the 180-degree rule was true for all triangles, regardless of what the triangle was shaped like. So what about if I had other quadrilaterals, like a trapezoid? So I went ahead and measured those angles, and sure enough, they added up to 380 degrees, 360 degrees. And I kept on trying with lots of different types of quadrilaterals just to see. And I found one quadrilateral where it didn't seem to work. And that quadrilateral looked something kind of like this. So it had 4 sides. And when I measured this angle, this angle, this angle, and this angle, it added up to less than 360 degrees, and it was actually significantly less. So I want you guys to take a look at it and see if you can figure out why this quadrilateral followed a different rule than all of these other ones that I've drawn. And so after I made the clarification that it has to be all of the interior angles, so rather than measuring this exterior angle, I should have measured this interior one. Then I saw that the angles of a quadrilateral all added up to 360 degrees. And then I decided to extend it a little bit further. And I was like, okay, well, if it's true for triangles and quadrilaterals, is it also true for pentagons if you have 5 sides? So I drew a couple pentagons and measured all of the interior angles. And sure enough, they all added up to the same number, which was 540 degrees. So then the next thing I wanted to explore was, okay, well, what about hexagons? If I draw a shape with 6 sides, do those angles consistently add up to the same amount? And when I drew a couple different hexagons and measured all of their interior angles, they did add up to a consistent number of 720. And at any point, I could have stopped my exploration And that's one of the things about experiencing math in an artistic way, is that it's basically however far you want your curiosity to take you. So if you keep on asking questions, you'll keep on discovering new patterns and new concepts in math. And you can also stop at any point. So I think it was around a hexagon or so where I was like, okay, it seems like regardless of how many sides it has, it's always going to be a consistent number. But then I got curious and I was like, I wonder if there's a relationship between the numbers. So I summarized all of the things that I'd learned, and I learned that if you have 3 sides on the polygon, all of the angles add up to 180 degrees. If I have 4 sides on the polygon, they add up to 360 degrees. If I have 5 sides, they add up to 540 degrees. And if I have 6 sides, they add up to 720 degrees. So before I share the pattern that I found, I want you guys to look at this and see if you can see a pattern between the number of side lengths that a polygon has and the degree measurement of their interior angles. So the pattern that I found was that the degree measurements each increase by 180 degrees. And so the way that I thought of it was just, well, however many side lengths you have, you would just add that number of 180 degrees from the triangle forwards. And I never wrote a formula for it or anything like that. And that was where my exploration ended. But later, about 2 years later, when I was in 8th grade, I found a formula in my math book, and I realized that this formula was describing the same pattern that I had discovered 2 years earlier. And I remember having this feeling of like kind of like fulfillment, where I was like, whoa, like this is so cool that I discovered something that was worthwhile enough to put into a math book. And granted, I'm kind of a nerd, so that's probably why I thought it was so cool. But the formula that I found in my math book said that the interior angles of an n-sided polygon, so n is the number of sides on the polygon, is 180 degrees times n minus 2. And I realized that this formula is describing the same pattern, because if you have 3 side lengths, 3 minus 2 is 1, and 1 times 180 degrees is this 180 degrees. If I do 4 sides minus 2, then I have twice as many of the 180 degrees, which is 360. And if I have 5 side lengths, or 5 minus 2 would give me 3, and 3 times 180 would give me this 540. And that's the same pattern as adding 180, because if you repeatedly add the same number over and over, that's the same thing as multiplication. So that was my first experience of having math be an artistic experience. And it wasn't necessarily the norm. A lot of times I was just doing whatever math my teacher told me. But the times that I found math to be the most fulfilling was when I was exploring something from my own curiosity. So in this class, I've tried to design some projects and activities that will help, kind of create the experience of viewing math from an artistic perspective and being able to look for patterns and describe those patterns. But ultimately, you guys will have the most fulfilling experience with math if you let yourself get curious about whatever topics we're learning. Like, ask yourself, why does this work? And how does this work? And if you have any questions you'd like me to help you explore, I'd be more than happy to do that, because I would really like you guys to have an experience of letting math be an art. So I hope that you guys enjoyed this story, and if you guys have any questions, we can answer those real quick before we go into talking about the syllabus.